So again, repeating is that we're going to do section 10, linear regression, and we're hopefully going to start doing a little bit of section 11, which will be multiple linear regression. Basically, really what we're going to be doing for our project 1, and really linear regression is like our first real machine learning algorithm. It's usually not considered a machine learning algorithm because there's so many more advanced things that we can do. So just kind of know that's like, usually people won't refer to it as machine learning, but it really is, and it's statistical learning. So we'll see what this looks like. And you guys may or may not have had experience with linear regression with other, subjects, maybe in college or, other experiences, right? So the first thing I kind of want to talk about is some basic stuff is covariance and correlation. And this will be useful for us analyzing when we do our linear regression model to say how good of a model it is. So covariance, I'm going to go this very quickly. Know the curriculum has a lot more information. But covariance basically is defining, if you remember variance basically, and variance is tied to standard deviation, right? Is that it defines basically how much a spread there is from the mean. So if we think about like a normal curve, our Gaussian distribution, basically our variance describes how much our values differ from the mean. So is there a lot of difference in there, or is there a small difference that tend to be all clustered around the mean? That's really what variance means. So covariance is kind of similar. It's kind of a play on variance. And you can see it's got a very similar structure because we have this xi and y j, and those are basically comparing two different features. So you might, for example, have a value in this number and then that similar value, or sorry, jumping ahead. If you imagine your data frame, so I'm going to quickly jump out, is if I have my data frame like this, and I have each data point, you might have multiple columns. Bless you.
Sorry, I'm not muted.
No problem. So I have my target value here. And then so this is I'll call it y. Sometimes we'll call it x1 or x2. And then we'll call this x. These x and y's are features. And so imagine for each data point right here, okay, so this is an ID number, right? There might be some value. Let's say this is 1, this is 2, and their target's I don't know, 1.3. Doesn't really matter what these values are. Basically, we're seeing how close are these x and y values together compared to each other. So you basically do this for each row. That's where that sum comes over. And you say basically how similar are they to each other. And this is actually really important as we do linear regression, because linear regression can be, what's it called? Can be affected if we have things that are very closely related. Now note for module 1, we're going to talk about what correlation means. That's where covariance kind of leads into. But note that for module 1 project, we're going to basically teach you how to deal with multicollinearity, basically when things are very correlated with this high covariance. And the way we're going to treat it is basically just get rid of it. But there's more advanced techniques as you go further into data science.
Pode pegar para ela, por favor.
Oh. So we have sorry, I got lost in my thought for a second. We have different techniques to do. For example, PCA will be one of the things for basically relieve some of that part. And we'll talk about this again, but I wanted to say that's why we're talking about covariance. Okay, let me go ahead. There we go. So I can actually, oops, nope. Sorry, Zoom moved all my windows over and now I can't, there we go. I couldn't write, or I couldn't click anymore. All right, so just know positive, covariance, basically saying how are they related. So we have a positive covariance, basically they are related to each other, okay? Basically, if one goes up, the other one goes up. That's what positive basically means, and positive covariance. And then we have negative covariance, where if one goes up, the other one goes down. So you might have an inverse relationship and stuff like that. But note that if you look at this equation, if you put in the numbers, you basically can go from negative infinity to infinity, which, I mean, it's okay, but it doesn't tell us exactly what strength, since we can have such a huge range of covariance. We want something that kind of minimizes what that range is so that we can treat it a little bit easier to compare different things. Like if I have a covariance of 500 and a covariance of 200 and a covariance of 2, do those actually matter? It's well, they're not really scaled together. They're hard to do it. So that leads us into something called correlation. And correlation basically, kind of going off of it, you can kind of see the similarity to covariance here with my definition up here. You can see correlation, and this is Pearson's correlation. There's multiple ways you can do correlation, but this is usually one of the most commons. This correlation R is kind of similar to how we look at our covariance. And this allows us instead of like defining it by the number of points and everything like that, we can instead basically shrink it down, that essentially like that covariance of how they relate to each other, to independent units. So now we're just going from -1 to 1. So that means it's easier for you to compare, you know, if you have like feature X1, feature X2, feature X3, feature X4, you can compare multiple features and use that correlation. And again, we go from -1, so negative correlation where one goes up, the other one goes down, and positive correlation where if one goes up, the other one goes up, or if one goes down, the other one goes down. That's both positive. Okay. Any questions on this generally? Correlation, covariance? Cool. Thumbs up so far? All right. And if you have any questions, just go ahead and stop me, right? So you guys probably have seen this if you've done any statistics. So correlation, you've probably heard the classic correlation doesn't mean causation kind of deal, same idea, is that we have positive correlation. This is perfect. It's not, this is from the curriculum, by the way. But it says perfect. It's maybe not perfect, but like the idea is that if you're going up by a certain amount, the other one will go up. And you can see here, it's like, well, this generally happens, but you can see sometimes they're a little bit lower. So ideally, if we go up like perfect correlation, a perfect correlation of 1 would mean that every time you move up a certain unit, the next one would also move up by that same amount or some factor of that amount. This one you can see sometimes if I move up, this one kind of went down. So you can see like went down on the y-axis here. And that's not quite positive, but it's pretty generally going in this upward direction. And then we can see there's generally a direction up this way, but not quite. This is no correlation, right? So basically randomness. This might even have, to be honest, might have a little bit of positive correlation in here. But basically a correlation of 0 would be completely random. Basically there's no relationship between them at all. Usually you don't have completely no correlation. Usually there's some correlation just by pure chance. In fact, if I ever got a correlation of r equals 0, I'd be really like what? Like that seems really strange. It's just unlikely to happen. You'll probably have a slight positive or slight negative, just kind of know that happens. And then obviously the negative you can see going in the opposite direction. Okay, so again, that's correlation. And I'll move on to our next part. So once we know those two parts, basically our covariance leads us into correlation, and our correlation allows us to kind of think about, like, all right, well, if a value goes up, maybe this other value goes up, and this leads us into statistical learning. So in statistical learning, basically, our idea is that we have our different variables, right? So we have our independent, our dependent, and our controlled variables. So if you're familiar with science, these are pretty classic. Basically, your independent is the one that you're adjusting. You know, we say we're adjusting, but like it changes something. And we usually look at one dependent variable. Sometimes we'll usually call this the target. Okay, so, and kind of using the terminology from like what we'll see in the future is we'll call these independent variables features and the dependent called target. And controlled variables, we don't really talk too much about controlled variables in this context, but if you imagine in science, we might have certain variables that are supposed to have no effect or that aren't supposed to change at all. So these are kind of things that we kind of ignore because we can't change them kind of deal. But the main thing for statistical modeling is you take information. In statistics, is really basically saying you're summarizing information, some data set, and you're taking that data set and you're using a function or a mapping that defines a relationship. So this is actually really important that we'll touch about basically all machine learning models in general, are statistical models in some way usually. And basically the whole idea here is that we're saying if you put in a data, if you say, I have this data point with, you know, these different features and I put it into my model, my statistical model, some kind of model, you put it in there, it will output saying it should be this target. And that's really what a statistical model is. It's a mapping. And we'll see this really true for machine learning. Now, kind of looking ahead is that our linear regression, you can kind of get probably why it's called linear is because we're dealing with lines. You can get more general, and that's when we start using more powerful machine learning algorithms to basically do other mappings. But then the end is basically saying, taking a bunch of points in with some features and outputting and say, what should the target be? That's essentially all machine learning, statistical modeling, all that stuff is. Of course, it's just how you get from here with all the features to the target is the hard part. Okay, but again, it's just defining a relationship. And so I know this drawing's a little small. We can see here, I think this is also from the curriculum, if I remember this right, but it's from the height versus weight. And so the idea is like if you increase, you know, your height, you are probably going to be heavier. But some people who are taller are not necessarily heavier than people who are shorter, right? Sometimes, you know, someone who's shorter, just maybe more stout, might weigh more. So you can see there's a little bit of fluctuation in here. Okay, and we'll see how to account for that fluctuation, especially in multiple linear regression, right? So this leads us into some terms. Like I said, features versus target. You can think of your features as your independent variables, your target as your dependent variable. And by convention, we usually put our target on the y-axis. Now this is usually when talking about like, 2-dimension, but also I guess in 3 dimensions, you would more likely call it like your z-axis, x, y, z, right, going up. But just know that we usually have our y-axis as our target variable, our dependent. What's the thing that's supposed to be affecting it? This is usually not too big of a deal because usually the target is just meaning like, what is the thing we're trying to predict, okay? And then we'll talk about using parameters. So basically every model can be adjusted and we adjust that with something called parameters. Basically, we're trying to figure out what are the right parameters to make our model fit our particular set of data, okay? And this, I kind of put this part right here. We talk about model validation. So like you could create a model and just say like, oh yeah, if someone's weight is, if someone's height is 5 feet, they should be 150 pounds. That right there is a model. But the idea is that we don't want to just like say something and then let it like that be the truth. And since we want to take the data and use that data to figure out is our model good, our model validation, we validate our model. And that's really the learning part. It's like if our model's no good at basically predicting on our data, then we need to adjust our model until it does fit better. We keep adjusting, tweaking a little bit back and forth. And that's really what the learning part is. This is why we really call it machine learning. You're basically trying to learn what the best way the model should fit. And when I say we, usually we're talking about a computer algorithm, figuring out how do we do that, okay? Is there any questions so far? I know I'm kind of going through this pretty quickly, but hopefully it's not feeling too quick or anything like that. Understandable so far? Yeah? Okay, cool. I see some head nods. No one's shaking their head. No one's looking too scared, so all good signs. So I did talk, sorry, I kind of skipped this part. So talk about learning model validation, and this is something that we'll especially get into when we do bigger machine learning algorithms, because linear regression tends to be more of the simpler one that we can kind of like, it's like, oh, I get how this works. But when we do model validation in general, basically we want to make sure that we call it training, is we want to teach our algorithm essentially based on some data. But then the problem is like, well, after you teach it, you have to test it out, right? This is where this training versus testing comes in. There we go. So the reason why we do this, like, well, okay, we have to have a certain amount of data to train on, you have a certain amount to test on. So for example, you probably know, like from school, if the teacher gave you basically a study guide and it was literally the test, right? And they just gave you that and said, all right, go ahead and learn this, and said, oh, by the way, this is going to be literally the test. As a teacher, you kind of hope that the students would probably get 100% or close to 100%, right? Basically, they learn the stuff on their CC ahead of time. They practice until they get that exactly right. Well, if they only use that practice test, which is going to be the test, if they only use that test to learn everything, right? If you give them a test that has some new stuff that's not on that study guide, and they've never looked at it or never even considered what that is, they just memorize the answers, then they're going to do poor on that. They're going to do poorly on that final test. So the idea here with validation is that we might split the data into training and testing, where basically we say, all right, here's some parts of the data, and hopefully we kind of randomly pick enough of it so it's not exactly the same. And we say, all right, learn from this amount of data. And then at the end of you learning from this data, you might iterate, practice, tweak a little bit. You're going to take the testing data and say, that's how we're going to really see how well you did. So that's where this testing and training comes back and forth, okay? And so that's kind of like the why you do it, right? Is that the reason why we're doing this is because we don't want to give it all the data and for it to learn really well on the data we give you, and then we give you some new information and it's completely wrong because it just never has even considered that possibility. So that's why we do this training, this splitting of training and testing. And the way we evaluate it, basically say, well, how do you know how they did it, how well they did, how well they did, is you use something called a loss function. And this is more general statistical learning, machine learning. But our loss function we'll see for linear regression is basically how close was our line to our points. And so if we see our model does a really good job predicting on each point, we say this really well. And we quantify that with a loss function. In this case, for our linear regression, we'll see it's something called RSS. But we'll get to that in a second. All right. So again, this is just intro to statistical learning. And basically, this is like all these parts right here, if you ignore this graph, all these parts apply pretty much to all of machine learning. And this is like the basics of like how machine learning works. It just comes down to like, how do you implement this? And so our first implementation is going to be linear regression, but you can get it to basically for any machine learning model, okay? So that leads us to our actual linear regression, right? Oops. So linear regression, and I kind of showed you a few pictures already. All you're essentially doing is you're taking a bunch of points and you're saying, all right, if I were to draw just a line through these points to predict them, how would I do this? And so the idea here is that, like I said about like height versus weight, is that maybe as someone gets taller, right, they should get heavier, right? So there's this general kind of like model, we call it, like basically saying, oh, if you increase your height by this much, you would increase your weight by this much. But of course, people aren't exactly that way, right? So you'll have some points that are kind of like some people who are a little bit, you know, heavier, even though they're taller, or maybe they're lighter, you know, they're heavier even though they're shorter, and then like they're lighter even though they're taller, things like that. That's the general idea of linear regression. And you might have learned this before in statistics. It's also called line of best fit. So hopefully that sounds familiar to you guys. But the main point basically is that we have a bunch of these data points going on here, and we're trying to figure out what's the best way we can kind of like average, say like, well, on average, how well, like we kind of go in this general direction. And we'll actually quantify exactly what that means by how well we go through it, okay? And the main reason why we tell about linear regression is that if you guys read the book Naked Statistics that was recommended, like you can see like it's like what do you call it? I think it was like the holy grail of like all statistics that you can predict it, is that linear regression was kind of like the go-to for like everything for the longest time. And we're just now having more models and stuff, like, well, I should say just now, but like we have a lot more sophisticated things that we can do. And so what's nice about linear regression is that it's relatively easy to implement. And so we can actually do a pretty decent job using linear regression. And when we get into more and more advanced models, machine learning models, that you can basically say, well, okay, how well did it do with linear regression? If it did it really well with linear regression, but our machine learning model takes a lot longer to do, your boss might, you know, like if let's say you're talking to your boss or something like that, or another team, and you say, okay, I did this linear regression, it predicts, you know, like 90% accuracy, but I can do this machine learning model and it gives a 92% accuracy, but it takes a lot more computation power and stuff like this. And then like, you know what, it's like 90% is just fine. Let's use the linear regression model because it's relatively quote unquote cheap to basically implement and everything like that. So this is one of the reasons why you might want to start with a linear regression model first, is to see how well you can do. And then if you're, lack of better words, like machine learning model doesn't do very well, like it's just bad, then you know what you can already do with a simple model like linear regression. Okay, cool. So this leads us into how do you create this line, right? And there's all these parts right here, and I believe, so kind of quick going through, is that the curriculum right now has gone through a little bit of a change, so I had to like replace some of the images. I believe this used to be at least in the curriculum. I actually don't know if it's still currently in there. So you just know that this might, a form of this might exist in the curriculum, but this is a pretty generic, like general picture of what you see generally when you talk about linear regression. But the main thing is that you have a line, and that's what this blue line here, and that's your model, okay? And then you can see these green points right here. That's your actual data. And your goal is to basically get a good line that will predict your data really well, okay? And the way we measure this is basically saying, how far are these data points, these green points, from the line? And so you can see here is that we'll usually talk about this line being y hat. So you'll see like right here, we'll call it y hat. And basically it's just a line. So it's just gonna be y equals, you know, if you think of it, mx plus b, sometimes I'll usually call like ax plus b. Or if I'm getting really generic or general, which you'll see again and again in machine learning, this is pretty standard right here, is w0 plus w1x. So you'll hear me sometimes call it weights. And this will be really important as we get into like, for example, neural networks and stuff like that. It's kind of the same concept, but just know basically you have a number, right? Plus another number times x, which is just, in this case, just one feature, one independent variable, okay? So as we adjust x, our y hat will adjust, and that's what this blue line represents right here, okay? But of course, our blue line, unless, you know, the data is really, really strange and fits perfectly on the line, we'll never be able to get it exactly on that line. So we want to know how well did it do, right? Because if I drew a line like this, is a pretty decent line that kind of follows those green points pretty well. But if I drew another line that looked like this, clearly this line is not as good, right, at predicting the data, right? But we need to quantify in some way. That way we can tell our computer algorithms, hey, this line's no good, do a better one, okay? And so the way we define that is something called RSS. And so let me undo. Okay, so you can see here, we have basically the distance from the line. So you can hear is that this point is like point Y, right, on this part of the axis. So you can say, okay, the distance from here to here is Y hat minus Y. In this case, we do absolute value because we're just talking about what's it called, how far it is. But we'll see there's some differences you can do. But the main thing is to say, all right, from here to here, how far is it? Basically Y hat minus Y, okay? And we just do absolute value. Later on, we'll see you can use squared, but basically get rid of that negative. We just want to say how far it is. We don't care if it's above or below, right? And of course, W0, it's just the slope. You can kind of see that hopefully from that equation from before, okay? Any questions about what's going on in this picture? I know there's kind of like a few things kind of being drawn, but the main thing you have to know is that there's this blue line right here, that is our model. It's represented by essentially some form of Y equals W0 plus W1 times X, or MX plus B, if you remember that from like back in grade school, but same concept. And then we can judge how good it is by seeing how much this vertical offset. We'll call these residuals in a second, but basically how far is it from the line? Okay, cool. So the big thing is like, okay, how good is it? And so this is when we actually do something called, the sum of squares. So, and it's actually the residual sum of squares. And so that's where RSS comes from. And essentially what we're going to do is we're going to say, how well is this going? Sorry, I replaced one of the pictures on here and I realized it might not be the best picture right now for this. But the main thing is what we're going to do, instead of just doing the absolute value, which is called their L1 norm, we're going to square it. And then we're going to add up those squares to say how good of it is. So you can say like this line right here, and you can say there's a little square. You'll see these kind of pictures like this, like these squares coming through. And we add up basically all of that area of the squares. So essentially what we'll have something is like Y hat minus Y. And that's for every point. And then we'll square this. So really I could have just put, I didn't have to put absolute value, but like we'll square this whole thing and then we'll sum up all of those points. So basically, how far is this point from here? All right, square it. How far is it from this point? All right, square it. And we'll add up all that together, and that'll give us a sum value. Okay, that's kind of what we're doing when you say sum of squares. All right. So this leads us into, and it's the residuals, right? This part right here is like how much it differs from the prediction. And so the thing is that you want to say, well, how do we do this? Well, we quantify it basically saying the worst model. And when I say like the worst model, it means like the simplest possible model ever. And what this line represents is basically just saying, if you average all of the data points, basically saying, you can think of like these are the Y being the weight. It's like, all right, like let's say the average weight for a person in the US is, I don't know, let's say 180 pounds. Okay, like about like 100 kilograms, right? So we have about that value and we say, all right, it's 100 kilograms. It's the average weight of someone. Every person, no matter how tall they are, they're 100 kilograms. And that'd be it. Like, obviously that's wrong, right? Because you have someone who's like, let's say a little kid who's like 3 feet tall. They're not going to be, almost 200 pounds. So that's why we talk about like the worst model, but it does well, it, quote unquote, does well enough, right? And that's what we compare it to. It's like, all right, what if we just took the average of the points? So you can see here, like this is we won't do this for linear regression, but you can see here's a parabolic kind of relationship. And you can see just taking the average is pretty crappy. Even this one right here is pretty bad, right? It wouldn't do very well at predicting overall. But we use that value and compare it. That's why we say we compare it to the worst model. And basically by comparing it to this quote unquote worst model, we can actually define some values. Sorry, I just realized, why does this keep happening? Sorry, I had a set of equations. I just realized that they're missing from here. But know in the curriculum that they actually, you can build this up. Basically, you take your sum of squares and you say, how much is it different from this worst model? And as you get better and better, you'll actually get something called your R squared value. And so your R squared value, and I'm not going to write it down because I'm not going to confuse you guys by writing it strange from the curriculum. But your R squared value is really what we come down to, is we compare basically how much does our residual. So actually, I'm going to go up just a little bit. Okay, so if you see right here, is basically we'll come up with something called our R squared value. And our R squared value is based on, I'm not gonna write the full equation because to be honest, I'll probably write it wrong just off of memory. I have to kind of work it out. That's how I always do equations. You think I would memorize things, but I don't memorize them very well, okay? But the point is, the R squared values is based around saying how good or how far were these points from my predicted Y value, right? My Y hat. So this gives us something called our RSS, okay? Our residual sum of squares, okay? And then we also compare it basically to, well, how far were the points from this really bad model? So if I drew this in a different color, that'd probably be better. So let's say write it in green here, is that these data points, data points are really far away from this. And some of them are really close, right? But a lot of them are really bad. And basically you say, okay, how much does this differ from our quote unquote worst model? And this will give us something called the R squared value. And what's nice about the R squared value is that the way we construct it, we'll actually get something that's between 0 and 1. Okay. And this is where a lot of people will mess up saying what an R squared value actually means. But in general, we say a higher R squared value means that your model is quote unquote better. But what we really mean by it is like when you have a model that is close to, basically close to 1, is that close to 100%, so like 0 to 100%, how much your residuals are explained by your model. So that's a key point. It's a little subtle, but it's saying, does your model explain the variance of your data points? And you can kind of imagine this, right? Like with, I said about like the weight versus height kind of deal, is that there might be some other factors besides just your height that affect the weight, right? So let's say this is my model right here. And that as you get taller, right, this is your height, this is your weight. As you get taller, you tend to weigh more, but in the real world, right, your data points will not follow this perfect line, right? Some people will be heavier even though they're shorter. Some people will be lighter even though they're taller, kind of deal. And so you might have something that kind of goes around this point. And so you have some variation. Well, some of that variation might be explained by the fact that maybe boys and girls have a different kind of, height and weight relationship. Maybe depending on other things like, where they live, for like basically what they're eating, or, what their age is. Maybe it depends on what age they are, right? So these are things that kind of factor in. But the point is, like, if my model has an R squared value of like, let's say like 0.9, that means 90% of that variation is explained by my model. Okay, there might be still some variation and stuff like that. Basically, like you can think of it like the fuzz, like the randomness that kind of hops around my model. That's not explained by my model, but a good portion, in this case, 90% of my model, or 90% of the variation is explained by my model. The way we can fix this, especially when you look into multilinear regression, is to factor in multiple features. And we can start adding in more features in this to help explain that fuzziness. So for example, in here, if I'm looking at just height and weight, it looks like just complete randomness around my model. But maybe if I factored in the fact that if it was a boy versus a girl, or what their age is, maybe then I can explain even more of my model. That randomness really wasn't random, it's just a feature I wasn't thinking about. Okay, so hopefully that kind of gives you an idea of what I mean by R squared. And in general, people always say like, well, how good of an R squared value should I have? And it all depends on the context. And also it depends on like what you're actually doing. Just because you have a high R squared value does not mean your model's good. It just means it explains much of the variation. So you have to be careful with that kind of subtleness. But usually like a 0.85 R squared value is considered pretty decent. Like that's pretty good by most standards. 0.7, usually that's pretty good too, depending on the context. Usually we like to shoot better than 0.7. If you get under 0.7, like if you're getting 0.5, usually most people kind of like say, no good. So just kind of get an idea, but it all depends on context. And sometimes you can get a 0.99 model like R squared, but in that case, I'd probably like squint a little bit, say, you can really explain 99% of all variation with a linear regression. I'd be like, that seems kind of suspicious. So just know, again, context. All right, any questions in general that I just kind of went over with R squared? I know unfortunately I didn't have the equation that I normally would have. I had to go back through my notes and make sure I didn't like delete a bunch of things I had previously. Yeah, cool. Thumbs up so far. And again, the curriculum has a lot more information that I'm giving you within this past like 30 minutes. So of course, there's a lot more you can get into it. All right, so this leads us into saying, okay, how do I know when a linear regression model works, besides my R-squared value, right? So these are the things, these are the criteria that you need to have essentially in order for you to say your linear regression, remember linear meaning line, works. One, it has, your data has a linear relationship. Makes sense, right? If you have no linear relationship, good luck trying to use a linear model to explain it. So kind of going back up to here is that if I try to explain this with any given line, it basically is impossible for me to draw a straight line and actually predict well on this kind of relationship, right? Obviously, I need something else, like something like a parabola, right? In order for me to model this. And we can do this. For example, in module 2, we'll talk about ways to modify our linear regression to basically be not so linear. There's some other things you can do too. We'll talk about transformations like log transformation and multiple linear regression. But there's some things you can do to help you modify your data to basically fit better into a linear pattern so you can actually have that relationship go through. So for example, this one, at first glance, this might say, hey, this is actually not that bad of a model, right? As you increase the value, but you'll see some subtle points on here. So for example, if you look at this really quickly right here, you can see like the data actually kind of spreads out like this. Okay, so first of all, it's like, okay, this is not like if I drew like a line in between like this part that averages, you'll see the line's not linear. In fact, it kind of goes into this kind of exponential and then kind of levels off kind of deal. You're like, okay, that's not quite linear. Okay, so that's something that you'd have to look out for. There's also some other things in here too. I don't know, what things might you notice that's not quite right with this model? Just glancing at it, besides it being kind of going up like this. And it's not an easy thing to, I don't think I would have got it if I didn't understand this beforehand. But one thing you might say is like, hey, all these points are really close together right here. And then as we get bigger, you can see they kind of spread out a lot more. This is an issue too. And this is where we talk about, we'll talk about in a second, but one of the things, so heteroscedasticity. I can never say that word correctly, but like, it's basically for us to figure out saying how well does our model predict over different values. So I just wanted to show you this picture first. That's why I had this before. But our model has to be linear. So step one, model has to be linear. Next thing is basically its normality. And this is a really tough one that a lot of people get wrong, including, I think sometimes I say this wrong. So I want to make this really clear, is that your data does not, your distribution of your data does not have to be normal, okay, in order for you to use linear regression. So your data itself does not have to be normally distributed. However, your residuals should be distributed normally, okay? Basically, the way I say this is a kind of a tough one, is that you can imagine is that if I had, this might be, I'm trying to see if I have a good picture now. Okay, let's say this part right here, is that let's say my model is really good at explaining this. If my model, if my data points basically follow on a normal curve. So if I imagine like it's like on here and I drew like just these points right here, with a normal distribution, if I turn it sideways, right, I would have like a whole bunch of points towards the average, right, towards the middle, and then not so many points on the edges here. I might have like 1, 2, but most of them will kind of be staggered in here and then they kind of go outward. This is generally what a normal distribution really means, right? So you can imagine like, okay, if my data is normally distributed and this middle part right here, that's my average, okay? That's where your linear regression is going through. So if you kind of imagine turning this on its side, and so if instead it kind of had like a normal distribution that looks something like this, okay? And it's centered on the line itself, you'd expect most points to be close to here and then further out over here. And that's what I mean by its residuals being normally distributed. Basically saying it's like, well, there's some points that are really far away, but they're not as many, like most points are pretty close to the middle. If instead most points were kind of like out here, okay, like it's skewed, okay, then I have an issue. It's like, oh, most points are over here, but my line goes through here and then it's spread out right here. That's not a normal distribution anymore, right? And this is what we talk about, like the residuals need to be normal, not the actual data, but just the residuals, okay? And so in this case, if you actually look at this line, if you ignore this first half right here, ignore this part, this is actually pretty normally distributed, like maybe more or less random, but there doesn't seem anything particularly maybe like abnormal. And you can actually graph out these plots. So this is actually what we have below, is that if I actually plotted out the residuals underneath here, and just know that this is from the curriculum again, this is not from any particular data set, is that if I plotted out these guys right here, you would actually see the residuals be spread out. So this right here is a normally distributed residual. So your residual, like, okay, residual of 1, residual of 2, residual of -2, and how frequently they have, that's our normal curve. And I realized, oh my gosh, what the heck? Sorry guys, I just realized I'm missing part. I don't know how I'm missing parts. Oh, good. It's just hidden by this part. All right, good. Whew. Now I'm wondering if I'm missing parts I didn't notice over whatever. Okay, I'm gonna move on. It's Tuesday. It's messing me up. All right. So anyway, one way we can do this through a histogram. Basically, plot out the residuals, see how well they're distributed. Another way we can do this, which is really useful, is a QQ plot. So QQ plots, you may or may not have. This is more of a more advanced statistics. I don't think most people would have done this in their high school statistics class, for example. But you can use a QQ plot basically that will plot the residuals and over this line. So you can see here, these are histograms of the data. And you can see here, for example, this is very high kurtosis. We talked about kurtosis last time, where it's very highly peaked. And you can see that we have a different kind of, what's it called? A different QQ plot here. And you can see here, this is not a normal distribution. In fact, it kind of has this tail, it's skewed off to the right? So like most of the values kind of end up kind of spreading out off to the side. And you can see this QQ plot here, we can actually see the residuals kind of going off. So this is a very quick, nice thing to do. So one quick thing I want to emphasize is that this is a visual test. Just like the histogram, this is not saying, oh, this is normal, like this is like say what value. This is basically doing us a very quick visual. And the reason why we do a visual is because you as a person can quickly tell, hey, this does not look normal to me. This does not fit a normal distribution. You very quickly to point out those patterns. So you don't have to do a formalized mathematical test for normality. You can just quickly look at the plot and say, all right, no good, or I have to do something to this data, or this data won't be good for a linear regression. So this is the reason why we do like visual plots, because again, people are really visual in the sense that you will pick up patterns very quickly. So there are tests for normality that we'll talk about in future times. But right now, I just want to show you that in general, we need a normal distributed residual data, or the residuals need to be normally distributed. Okay, cool. So hopefully hone in that. Again, data doesn't have to be normally distributed for linear regression, just the residuals. Okay. And so this leads us into our last thing, which is this horrible word that is way too long to pronounce, is heteroscedasticity. Sure, why not? Note that also, just for the heck of it too, you can also spell it, I believe, with a K instead of a C here. So they're just trying to mess with you the whole time. I don't know who came up with this word, but it does exist, all right? And you can probably break this down, hetero in the sense of being different, scedasticity, because long word, I don't know actually, but I'm sure there's some kind of Latin form of why this exists. But basically this is saying is that you're plotting your residuals. And so you can think of this plot right here as like, you can imagine like what the value of the residual is, it, +1, -1, kind of similar to like this right here, where we have our residuals positive or negative, and we're just seeing where they exist. And this right here is our X factor, our feature, basically saying, as I increase these parts at X, where do the residuals lie? And so you'll notice is that here the residuals start off really small, but as we increase this X feature right here, our residuals get more varied, right? So this is heteroscedastic. And same way from this way is that we start off with really high residual, the residuals are very big and they narrow down, okay? Versus a homoscedastic pattern, right? Is that we basically have here is that our residuals don't change, like the pattern of our residuals. Basically, some are really big, some are really small, but in general, you don't have this difference, okay? And you can see something similar here is that, for example, we have a homoscedastic relationship here, or at least pattern. And then here we have a heteroscedastic, so you can see that the residuals get larger as we increase our X. And here we can see something even funkier, which is, in this case, a nonlinear thing. This is not heteroscedastic, but it's also not homoscedastic. I don't know if you guys can actually call this heteroscedastic. I could be wrong on the definition, but in general, we say like, oh, that's clearly not a linear equation. So note that this heteroscedastic does not mean the data is not linearly distributed. So just to kind of prove my point here is that this one right here, if I ignore this first part, this would be a heteroscedastic, right? Our residuals increase as we increase our X right here. So you would have that pattern where it kind of balloons outward. In fact, it looks if I were to plot out this residuals, it would look probably close to this one right here. Okay, and that's because the residuals start off pretty small, and then as we increase our X factor, or our feature, we can see that the residuals get much larger. Okay. So those are our three conditions. It needs to be linear, needs to be residuals need to be normal, okay, and it needs to be homoscedastic. All right. So our residuals need to stay the same amongst our linear regression. All right. Any questions on anything that we had talked about for linear regression? Okay, cool. Thumbs up, thumbs down, that works. All right, cool. And so this will lead us into, well, okay, so kind of going on here, nice little two-dimensional stuff. And because we're data scientists, we don't always work with two-dimensional data, meaning that there's one feature, one target, because the world is much richer than that, right? And so this is what leads us into multiple linear regression. In fact, this is, I think even in the curricular calls, simple linear regression. So just to kind of say, oh, this is the simple linear regression part. Basically, it just means it's like, oh, we're only looking at one feature and one target, right? And so multiple linear regression will actually look at multiple features for one target, which kind of makes sense without the world. Just like I talked about, like weight. Weight would probably rely on multiple features, right? Maybe you measure your metabolism. Maybe you measure the fact that they're a woman or a man, right? Besides just their height.